Hey there, I'm going to work a couple problems from our Dynamics 2 sheet. So number one, it says we have a 4 kilogram block. It's at rest. Remember, we always want to underline the word at rest. And it's on a rough table, so that's going to indicate that we have some friction involved. It's pulled to the right by a horizontal string, has 25 newtons of force, and for 4 seconds. And it says that the coefficient of kinetic friction is 0.25, and we're asked to find the final velocity of the block. So we always start out with our free body diagram, and for this one, we're going to have, obviously, our FG goes down, and since we're on a surface, we're going to have the normal force going up. It's being pulled to the right by tension, and then there's going to be a little bit of friction, and we'll put kinetic friction on there. Now we're asked to write down the quantities that are given and needed. So looking at what was given, it says that the mass is equal to 4 kilograms. Now we also know that the weight is mg, so the weight here is equal to 40 newtons. And the problem gives me the tension. It's equal to 25 newtons. My coefficient of kinetic friction is equal to 0.25. Time is equal to 4 seconds. And then we underlined it started at rest. So that means that your initial velocity, this v naught, is equal to 0 meters per second. And then we're asked to solve for the final velocity v. So once we make our free body diagram, remember we always make our net force equations. Okay, so for my net force equation in the x direction, it's going to be tension minus my friction. And in the y direction, it's going to equal normal force minus Fg. Now, vertically speaking, we are balanced. And so there's my two net force equations. Now, the final answer we're trying to solve for is the final velocity. And so thinking of an equation that can help me find the final velocity, we know what we learned in class before when we had our velocity time graph and we found the slope and is equal to acceleration. And that's when we talked about our acceleration is equal to the change in velocity over time. And I can rewrite that equation for acceleration as acceleration is equal to your final velocity minus your initial velocity over time. So this equation will help me solve for my final velocity. And looking at it, I know the initial velocity, okay, and I know my time, but I don't know the acceleration. Okay, so to find my acceleration, I'm going to have to use Newton's second law. Okay, Newton's second law says that it's equal to my net force divided by the mass. Now I know the mass, but I don't know my net force. So I'm going to have to use my net force equation up here to solve for the net force. And looking for my at my net force equation, the problem gave me tension, but the problem did not give me my friction. So we got to find our friction, our kinetic friction. And we do have an equation for your kinetic friction. And if you remember from last unit, it's equal to the coefficient of kinetic friction times the normal force. So I have my coefficient of kinetic friction. Yeah, my normal force, the problem didn't directly state it, but because we're balanced vertically, as indicated in this net force equation, we can solve for the normal force. Okay, so that's going to be my starting point. Okay, so you always want to write out what's given, make your free body diagrams, make your net force equations, and then you can start looking at all the different equations we have to solve for to find our starting point. So that's going to be my starting point. So based off that net force equation in the y direction, your normal force is going to equal the weight of the object which we said was 40 newtons. So now we can solve for the kinetic friction. So for over here, my kinetic friction is going to equal the coefficient, which was 0.25, times your normal force, which is 40 newtons, and that's just going to equal 10 newtons. Okay, so now we have our kinetic friction, so we can solve for that net force. Okay, up here we can solve. So the net force in the x direction is equal to the tension, which the problem stated was 25 newtons, minus my kinetic friction, which is 10 newtons. So the net force is just equal to 15 newtons. So now we know the net force. We could put a check mark there so we can solve for our acceleration. Okay, and so using Newton's second law, the acceleration is going to be your net force, which is 15 newtons, divided by the mass of the object, which is 4 kilograms. So my acceleration is going to equal 3.75 meters per second squared. So we have our acceleration. Now we can go in and use this first equation that we indicated and solve for that final velocity. So let's rewrite that equation that we had up there. We had acceleration was equal to v minus v naught all over t, and we're going to solve for that final velocity. So I'm going to multiply both sides by t and then add the v naught over. So your final velocity is going to equal the initial velocity plus a times t. Now we can just plug in our values. Okay, so the initial velocity, it started at rest, was 0. And our calculated acceleration was 3.75 meters per second squared. And the time was 4 seconds. Okay, so this seconds will cancel out one of those. And so your final velocity is going to equal 15 meters per second. And there's my final answer. And the other part here just says to list some of those steps that we follow. Okay, so if we kind of summarize that, we wrote our free body diagram, and then we made our net force equations. Then we solved for our friction, right? That was the first thing that we did. Once we had our friction, then we were able to solve for our net force. And then after we had our net force, we used Newton's second law and we solved for acceleration. And then our last step was we solved our final velocity. So that's kind of the steps we took in solving this problem here. Now let's look at number 2 now, and we'll kind of work through number 2. So number 2 says we have a 140 Newton bucket. It's pulled directly upward by an ideal spring, and the spring constant is 800 newtons per meter, and it causes the bucket to have a downward acceleration of 2 meters per second squared. And we're asked to calculate the stretch of the spring. So let's start out with that free body diagram. So here's my bucket, and it's being pulled up by a spring, but it had a downward acceleration. Okay, so that means that your weight should be longer than the spring because it has a downward acceleration, so it should be unbalanced pointing down. Now we'll list our given quantities. So they gave me the weight. So it said the weight is equal to 140 newtons. We'll go ahead and write down the mass here. It's 14 kilograms. And they told me the acceleration is equal to 2 meters per second squared, and that's down. Okay, it's going downward. And then it also gave me my spring constant, K, which was 800 newtons per meter. So there's what was given to us. And we're asked to solve for the stretch, X. So we'll go ahead and make that net force equation real quick. Now, if you remember last unit, I had talked about how we can call our positive and negatives whatever we want as long as we're consistent within the problem. Okay, so since it's accelerating downward, I'm going to make it easy on myself, and I'm just going to call down positive. And so my net force equation in the y direction here is just going to be Fg minus the force of the spring. And so from here that we're asked to solve for this stretch. Okay, so thinking and how we can do that, we have Hooke's law, right? Force of spring is equal to Kx. And this problem gave me my spring constant, but I don't have the force of the spring. Okay, so to figure out the force of the spring, looking at my net force equation, I have a Fg, but I don't have the net force. So how can we find the net force? Newton's second law. Okay, Newton's second law says that it is equal to the net force divided by the mass. And so we can rearrange this equation, right, for the net force, because the problem gave me the acceleration and it gave me the mass. So if we rewrote this, it would be the net force is equal to the mass times acceleration. So we can plug these in. The mass was 14 kilograms. And then your acceleration was 2 meters per second down. But since we're calling down positive, I can leave that as a positive 2 there. And my net force then is just going to equal 28 newtons. So now, looking at that net force equation, we have the net force, we have the weight, so we can solve for the force of the spring. So if we rearrange that equation up there, that net force equation, I could add the force of the spring over and then subtract the net force. So rewriting that, the force of your spring would equal Fg minus your net force. So my force of spring is equal to 140 newtons minus your net force, which is 28 newtons. So the force of the spring is just 112 newtons. So now we have the force of the spring, we have that spring constant, and I can solve for the stretch. So your stretch is going to equal the force of a spring divided by your spring constant. So 112 newtons divided by 800 newtons per meter. And you end up with 0.14 meters. And so now we can summarize what all we did just now and the steps that we took. Okay, first thing we did is we made our free body diagram. We made our net force equations. And then we found and we solved our acceleration. Or I'm sorry, we solved our net force. And then once we found our net force, we solved for our force of our spring. And then the last step, we used that Hooke's law and we solved for our stretch. So in these problems, it's really good to write down all this information. Make your free body diagrams, make your net force equations, write down what the problem gave you, what you're looking for, and that'll help you in identifying the different equations that you're going to need to solve for this problem that you're working with.